All right. Third segment of our week 6 physics online. We're going to look at light. In the previous video segments, we looked at waves in general, how they can be transverse or longitudinal. And then we looked at longitudinal as being sound. And now we look at transverse waves where you have the, I guess, very normal crest and trough. How you would end up, that is kind of associated with light. Not going to spend a whole lot of time talking about the history, but we do have to look at the two main parts of what light is, because Newton did experiments on light, and what he found out was that white light from the sun can be broken into the colors of the rainbow. So he sent light through a prism and saw that it breaks into the different colors, meaning that light itself has different wavelengths. So if we say it's the wave theory, so we say Newton basically comes up with the idea that light behaves like waves and can then be spread apart based on different wavelengths. But Einstein comes along in the early 1900s and says, well, it does do that, but it also moves like a particle, which means it has a pressure, like it's a particle that can hit you. And we always talk, lasers have the ability to cut through things. So if you focus the light and you get it streamlined, that you can actually use that as a pressure. So it's a particle, not just a wave. And that's what we call the duality of light. So both scientists were correct, and probably two of the most brightest scientists in the entire history of the world, Newton and then Einstein, gave us this idea, the duality, that it is a wave and it is a particle. It's both of them. So it explains all parts of the wave. The history of where about the speed of light came from, I don't care that you necessarily know that or read up on it, but what you have to be able to do is know the speed. The fact that speed is 3.0 times 10 to the 8th meters per second. That's the important part. And speed of light doesn't change, basically. It does change slightly as it goes through mediums, but as it goes through gases and things. But for the most part, it's 3.0 times 10 to the 8th. It doesn't change much. And when you're talking about large distances, it takes time to get here. So light travels, 8 minutes to get from the sun to here. If you're talking about short distances, like if I flip on my light switch, it's instantaneous for us because it moves so fast. And that's kind of the important part with the speed of light. Light itself, though, it's alternating. It's an alternating electric and magnetic field. And that's why we will call it electromagnetic waves. And light, specifically visible light, is only one portion of that electromagnetic wave. So if you look here, we have one direction. You have an electric field that has a crest and a trough, but then also simultaneously at a 90-degree angle to that, you get a magnetic field that would have a crest and a trough. So they kind of coincide with each other. That's why we call them EM waves. And light is just one specific part of it. And we'll see here on this one, we get to light. This is only what we can see. Like when sound, last segment, we talked about sound, and sound, as far as the threshold of what we as humans can hear, is 20 to 20,000 hertz. Our threshold of sight, that our eyes are able to see the wavelengths, only between 400 and 700 nanometers. Small, tiny little portion in there of what is the entire electromagnetic spectrum. Things like AM, FM radio, microwaves, ultraviolet light, X-rays and gamma rays. We know ultraviolet, we always hear that coming from the sun. That's the stuff we want to block with sunscreen because it's more dangerous. That has to do more with the idea that light still acts not only as a wave, but as a particle. And the higher up you are on this scale, as we're showing, which is actually the smaller the wavelength, the higher the frequency, the more dangerous, the more energy that wave actually has. So lowest frequencies that we can see is light. The highest frequency is going to be violet. Infrared goes down. Ultraviolet goes up. As we look at, I'm not going to get into all the interactions. They're on your main PowerPoint that I gave you, but